Today we'll begin our discussion on the next topic in the specialized area of pre-stressed concrete structures that are considered to be advanced civil engineering structures, and the topic is pre-stressing technology, that is essentially the pre-stressing techniques or mechanisms, that is methods that are employed in the civil engineering industry or the construction industry for pre-stressing concrete. Therefore, beginning our discussion on the pre-stressing techniques or methods of pre-stressing concrete that are typically employed or implemented in the pre-stressed concrete structures in the construction industry. The various methods or mechanisms used for pre-stressing concrete can be classified into two fundamentally different or distinct categories. That is, one, pre-tensioning, in which the steel is tensioned prior to the casting of concrete. And a general schematic diagram or figure illustrating commonly implemented method of pre-stressing concrete that can be classified as pre-tensioning of concrete is illustrated in the present slide. The particular or specific method of pre-tensioning concrete is termed as the long line method or the Hoyer's method of pre-tensioning based on the developer or the propounder of the particular long line method of pre-tensioning, that is E. Hoyer. And in the long line method of pre-tensioning, for which the schematic diagram or figure is illustrated in the present slide, steel wires or bars are first tensioned between end blocks in a apparatus termed as the pre-tensioning bed, wherein steel wires or tendons or bars represented by the green lines are first tensioned between the two end blocks, subsequently wooden or steel molds, that is formwork, are positioned or installed around the pre-tensioned steel wires for the purpose of pouring the concrete into the wooden or steel molds or formwork represented by the dashed lines in the schematic figure. After which fresh concrete or wet concrete is poured into the formwork or the wooden or steel molds, finally the steel wires are cut using an oxyacetylene torch after the casting and hardening of the concrete in the formwork or the molds, that is, after a sufficient period that is required for hardening of the concrete poured in the formworks of the molds, that is the minimum time for concrete to attain a certain compressive strength, typically the 21 or the 14-day strength. Thus, releasing the pre-stressing steel wires by cutting them at the ends using oxyacetylene torches as a general practice. In order to contract against the hardened concrete, that is considered to have attained the requisite sufficient compressive strength, typically the 14-day strength or the 21-day strength after the pouring or casting of concrete. As a result, the pre-stress that is generated in the steel wires by virtue of pre-tensioning the steel wires against the end blocks is transmitted to the pre-stressed concrete beams and column specimens that are cast and hardened in the formwork or the molds upon cutting the steel wires, the pre-tensioned steel wires at the ends using oxyacetylene torches. By the simple mechanism of pre-tensioning, wherein the pre-tensioned steel wires upon release or cutting at their ends contract against the hardened concrete column or beam elements, thus transferring the pre-stress or the pre-stressing force induced by the pre-tensioning of the steel wires against the end blocks and termed as TP, that is T subscript P, where the notation T signifies tensile force, while the subscript P signifies that the tensile force capital T is due to the pre-tensioning of the steel wires or the steel bars prior to the casting and hardening of the concrete. Consequently, pre-compressive stress, termed as pre-stress, is induced in the pre-stressed concrete elements such as the pre-stressed concrete beam elements and the pre-stressed concrete column elements shown in the schematic diagram for the pre-tensioning or pre-stressing bed, typically implemented in the long line method of pre-tensioning or the Hoyer's method of pre-tensioning concrete. Due to the contraction of the steel wires against the concrete elements, in summary, the pre-tensioning operation, wherein the steel is tensioned prior to the casting of concrete in the pre-stressing bed, results in self-equilibrating internal stresses of desired magnitude and distribution. After the pre-tensioned steel wires or bars are cut at the ends, thus generating a pre-compressive stress in the concrete elements termed as pre-stress, and a corresponding equilibrating pre-tensile stress due to the pre-tensioning force capital T subscript P in the steel wires. Due to the contraction or the tensioning of the steel wires termed as pre-tensioning against the concrete. The second method of pre-stressing concrete that is fundamentally different from the pre-tensioning method for pre-stressed concrete is the post-tensioning method. And as the name suggests, the post-tensioning method of pre-stressing steel is one in which steel, termed as the post-tensioning steel, is tensioned against the concrete after the casting and hardening of the concrete, in contrast to the pre-tensioning method of concrete. The other fundamental mechanism employed or implemented in the construction industry for pre-stressing concrete, wherein steel is tensioned prior to the casting of concrete. The second method of pre-stressing concrete is the post-tensioning method, in which steel is tensioned against the concrete after the casting and hardening of concrete. And a typical scheme for post-tensioning of a pre-stressed concrete beam is shown in this schematic figure or diagram, wherein a concrete beam is first cast by pouring wet or fresh concrete into molds or formwork that are provided with hollow ducts of a state or curve profile, that is, the concrete is poured into the formwork or the mold for the concrete beam that is to be prepared. With the formwork provided with a hollow duct that is illustrated by the light green lines that may have a straight profile or a curved profile, such as the parabolic profile shown in this schematic figure. Subsequently, the concrete is poured and cast in the formwork provided with the hollow duct or the straight or the curved profile, after which, in the second step, steel cables are passed through the hollow ducts in the pre-stressed concrete specimen, thus cast. In the step C, that is the third step, the steel cable that is passed through the hollow duct in the thus cast pre-stressed concrete beam specimen is anchored at one end using a generic washer and nut kind of assembly or any other proprietary anchoring mechanism. Subsequently, in the fourth step, that is step D, the steel cable that is thus passed through the hollow duct in the precast pre-stressed concrete specimen is tensioned at the other end, which is termed as the jacking end, as opposed to the anchoring end at which the steel cable is or was anchored in the previous step. Thus, tensioning the steel cable or the tendon at the jacking end using a jacking device, for example, a hydraulic or a pneumatic jack, generally a hydraulic jack, that tensions the steel cable at the jacking end against the anchor at the anchoring end as well as the concrete in the pre-stressed concrete specimen. Once the jacking force that is required to generate the post-tensioning force or the pre-stressing force, denoted as capital T subscript P, where the notation capital T signifies tensile force or pre-tensile force, while the subscript P signifies that the tensile force capital T is due to the pre-stressing or the post-tensioning operation. In this method of post-tensioning is achieved, the cable or the post-tensioning tendon is anchored at the jacking end also, as well as the anchoring end against the concrete using a generic washer and nut assembly or any proprietary anchoring system, that is, any proprietary or patented post-tensioning anchoring system. As a result of the post-tensioning operation explained herein, the post-tensioning of the steel, that is tensioning of the steel against the concrete after the casting and hardening of concrete, induces self-equilibrating internal stresses in the concrete that are typically pre-compressive or compressive, and tensile or pre-tensile stresses in the post-tensioning steel that are in equilibrium with the pre-compressive stresses in the concrete, in the pre-stressed concrete element. Thus, completing the post-tensioning operation resulting in the post-tension pre-stressed concrete beam element shown in the schematic diagram in the present slide. Proceeding to the next topic in the area of pre-stressed concrete technology, as part of the component of this course, CVL 443, based on pre-stressed concrete structures, the structural benefits or advantages of pre-stressed concrete, abbreviated as PSC, in comparison to reinforced concrete, abbreviated as RC, may be summarized by the structural effects of pre-stressing concrete and the consequent advantages and benefits in the structural performance of pre-stressed concrete, that is PSC versus reinforced concrete or RC, in terms of the design practice or the structural behavior of the pre-stressed concrete element in comparison to the corresponding reinforced concrete element. And the structural advantages or benefits of pre-stressing concrete in terms of the structural performance or structural design practice in comparison to reinforced concrete are as follows. 1. In case of fully pre-stressed concrete elements, the concrete section is more effectively utilized, since pre-stressed concrete structural elements can be designed to remain uncracked or even free from tensile stresses in the working range of loads, that is, in the range of working stresses under working loads or service loads, by design, in contrast to the reinforced concrete or RC elements which crack under working loads. As an elementary example of the simplest pre-stressed concrete structural element, that is a pre-stressed concrete bar, one may recall that the pre-stressed concrete bar can be designed to remain uncracked, that is, to achieve an uncracked concrete section in the range of working loads under the application of an externally applied tensile force denoted as capital T, where the range of the externally applied tensile force capital T is between 0 and the maximum working load or the maximum tensile force corresponding to the range of working loads or service loads denoted as capital T subscript W, where the subscript W signifies the range of working loads. In other words, the pre-stressed concrete bar, that is the most elementary example of a pre-stressed concrete structural element, can be designed to remain uncracked in the elastic range of behavior or the linear elastic range of stress strain behavior under service loads or working loads. In contrast, the corresponding reinforced concrete bar of identical geometry, that is, identical cross-sectional dimensions, for the prismatic cross-section and composed of identical grade of concrete, cracks in the range of working loads. Simply because a reinforced concrete bar cannot be designed cost effectively to remain uncracked in the range of working loads or service loads, since the cost of designing a corresponding reinforced concrete bar to remain uncracked in the range of working loads or service loads would be prohibitive. Therefore, the corresponding reinforced concrete bar or RC bar upon the application of the externally applied tensile force denoted as capital T would crack in the range of the working loads prior to the externally applied tensile force T reaching the maximum value corresponding to the limiting value of the range of working loads or service loads. Simply because the reinforced concrete bar cannot be designed cost effectively to remain uncracked on the application of the externally applied tensile force increasing from 0 to the maximum value of the externally applied tensile force in the range of the working loads or the service loads, denoted as capital T subscript W. Therefore, as the externally applied tensile force capital T increases from 0 to the maximum value corresponding to the maximum working load or maximum service load in the range of working loads or service loads denoted as capital T subscript W, the reinforced concrete bar will experience cracking of concrete at the most critical location. At the first cracking, followed by development of several additional cracks at other locations on the increasing values of the externally applied tensile force T. As discussed earlier in one of the previous slides, prior to the formation of the first crack in the range of working loads or service loads, in the reinforced concrete or RC bar, the externally applied tensile force is resisted or shared by the concrete, and the steel reinforcing bar in proportion to the axial tensile stiffness of the concrete and the concentric steel reinforcing bar as depicted in this figure. With the sum total of the share of the externally applied tensile force resisted by the concrete in the uncracked reinforced concrete bar and the share of the concentric share of the externally applied tensile force resisted by the concentric steel bar, denoted as capital T subscript S, proportional to the axial tensile stiffness of the concentric steel bar and the concrete section. Subsequent to cracking, that is the formation of the first crack and the subsequent cracks in the concrete in case of the reinforced concrete bar or the RC bar, as discussed earlier, the externally applied tensile force that is shared by the concrete in case of the reinforced concrete bar subsequent to cracking at various locations reduces to zero at each and every location of the discrete crack, as depicted in this third figure for the reinforced concrete bar that illustrates the distribution of the externally applied tensile force, capital T, between the cracked concrete, represented by the green shaded regions, and the share of the externally applied tensile force, denoted as capital T subscript S, that is resisted by the concentric steel bar. As depicted in this figure and discussed earlier in quite some detail, at the location of the discrete cracks, after the development of several cracks, that is, in the concrete of the reinforced concrete bar, the concrete is unable to resist or transmit any tensile stress across the cracks, and therefore the tensile stress is picked up by the concentric steel bar at the discrete locations of the individual cracks in case of the reinforced concrete bar after cracking. In any case, since concrete is unable to resist or transmit the axial tension or the applied axial tensile stress or the externally applied axial tensile force across the cracks in case of a cracked reinforced concrete bar, even though the externally applied tensile force T is transmitted across the cracks by the concentric steel reinforcing bar, the effective area of the reinforced concrete section resisting the externally applied tensile force T is significantly diminished or reduced at the location of the individual cracks, since the effective area of the concrete section at the discrete locations of where the individual cracks are formed is dictated only by the transformed area of the cracked concrete section, given as the modular ratio M times the area of the steel reinforcing bar A subscript S, based on the concept of transformed concrete section. In summary, the effective area of the reinforced concrete bar or the RC bar that resists the externally applied tensile force and transmits the externally applied tensile force T across the bar is governed or contributed only by the transformed area of the concentric steel bar, also termed as the transformed area of the cracked concrete section, given as M times AS, while prior to cracking, the effective area of the reinforced concrete bar, that is prior to the formation of the first crack, consists of the area of the concrete section as well as the transformed area of the concentric steel bar. In conclusion, the effective area of the reinforced concrete bar after cracking of concrete is significantly reduced or diminished, consisting of only the transformed area of the concentric steel bar and thus the concrete section is not effectively utilized in resisting the externally applied tensile force in case of the reinforced concrete bar, since only the concentric steel bar contributes to the structural resistance of the reinforced concrete bar subsequent to the formation of the cracks. In contrast, in case of fully pre-stressed concrete elements, for example, the pre-stressed concrete bar, the most elementary example of a pre-stressed concrete structural element, that is or can be designed to remain uncracked in the range of working loads, the concrete cross-section is more effectively utilized, or in fact completely utilized, in case of the pre-stressed concrete bar that is designed to remain uncracked in the range of externally applied tensile force capital T up to the limiting value corresponding to the maximum working load or the maximum service load. Continuing our discussion on the structural benefits or the structural advantages of pre-stressed concrete in comparison to reinforced concrete elements, the most fundamental structural benefit or advantage of pre-stressing concrete is that in case of fully pre-stressed concrete elements that are designed to remain uncracked in the working range of loads, that is, the range of working stresses under working loads or service loads, the concrete section is more effectively utilized, as illustrated in the previous slide, considering the example of the pre-stressed concrete bar element that is designed to remain uncracked in the range of working loads, that is in the working stress range under working loads or service loads, by selecting an appropriate value of the pre-stressing strain or stress, that is the pre-compressive strain or the pre-compressive strain, stress, also termed as the pre-strain or the pre-stress in the concrete prior to the application of the externally applied tensile force. Proceeding to the next example that illustrates the first and foremost structural advantage of pre-stressed concrete in comparison to reinforced concrete, we will consider the elastic behavior of pre-stressed concrete or PSC beams, that is an instance of a pre-stressed concrete structural beam element which is more advanced or evolved structural element than the previously considered pre-stressed concrete bar element. In the previous slide, since a beam element is defined as a structural element that resists or is subjected to flexural or bending stresses. Therefore, in order to illustrate the structural advantage or structural benefit of pre-stressing concrete in the pre-stressed concrete structural beam element, let us consider a simply supported beam with a span length capital L that is subjected to a uniformly distributed load, abbreviated as UDL, of intensity denoted as small q in kilonewton per meter, for example, in SI units, that is pre-stressed with a single straight tendon that is illustrated by the dashed green line in this figure. With a single straight tendon provided at an eccentricity E with respect to the centroidal axis of the simply supported beam or its prismatic rectangular cross section, where E in general, that is the eccentricity of the pre-stressing tendon, that is assumed to be a single straight tendon in the present example, may in general be a function of x, as in case of curved tendon or curved profile of the pre-stressing tendon, if applicable. However, in this present example, the simply supported beam with the span length denoted as capital L, subjected to a uniformly distributed load of intensity Q in kilonewton per meter, is provided with a straight tendon. Therefore, the eccentricity function, that is the function that describes the eccentricity of the pre-stressing tendon or the pre-stressing cable with respect to the centroidal axis of the simply supported beam and its prismatic rectangular cross section is a constant, since the simply supported beam is provided with a straight tendon. Therefore, our objective in the present discussion is to demonstrate that the pre-stressed concrete simply supported beam element displayed in the figure on the present slide can be designed to remain uncracked within the working range of external load, that is the externally applied uniformly distributed load Q, in the range of the externally applied uniformly distributed load of intensity Q between 0 and a maximum limiting value Q subscript W, where the notation Q signifies the uniformly distributed load, while the subscript W denotes the maximum working or the service load within which the simply supported pre-stressed concrete beam element considered in the present example is to be designed to remain uncracked or even free from tensile stresses. Worthwhile to mention here that the uniformly distributed load, abbreviated as UDL, of intensity denoted as small q in kilonewton per meter, for example, in SI units, in practice represents the permanent dead load due to the self weight of the pre-stressed concrete beam element and the live load due to the superimposed loads or imposed loads acting on the practical pre-stressed concrete beam. Therefore, to summarize, the objective of the solved example we are required in the present solved example to select an appropriate value of the pre-stressing force denoted as Tp in the single straight pre-stressing tendon or cable with a straight profile, as well as the constant eccentricity E of the pre-stressing tendon or the straight pre-stressing cable, such that the selected combination of the pre-stressing force Tp, that is capital T subscript P, where the notation capital T represents tensile force while subscript P signifies that the tensile force is due to the pre-stressing of the straight tendon or the straight cable. And the constant eccentricity, that is the eccentricity of the pre-stressing tendon or pre-stressing cable, which is uniform or constant along the span of the pre-stressed concrete beam, since the pre-stressing tendon or the cable has a straight profile, such that the normal or the direct bending stress, or the normal or the direct flexural stress, denoted as sigma x, where the notation sigma denotes normal or direct stress, while subscript x denotes that the normal or direct stress is along the centroidal axis x of the pre-stressed concrete beam at the midspan, that is x equal to 0, for the selected coordinate axis x, y, and z, with the origin assigned at the midspan on the centroidal axis of the pre-stressed concrete element, and the y coordinate equal to minus d by 2 for the choice of the coordinate axis and the origin. At all locations in the cross section, Z is less than or equal to the cracking stress or the cracking strength of concrete, sigma CR, notation that has been explained earlier, where the cracking strength of concrete is typically in the range of 5 to 10% of the characteristic compressive strength of concrete. Therefore, our question statement or the design parameters in case of the solved example is summarized by equation A, which implies that the normal or direct bending stress sigma x at the midspan of the pre-stressed concrete beam and in the extreme tension fiber the location represented by the coordinates x equal to 0 corresponding to the midspan of the pre-stressed concrete beam, and y equal to minus d by 2 corresponding to the extreme tension fiber. For the choice of the coordinate axis x, y, and z selected for the analysis, should not exceed the cracking stress or the cracking strength of concrete that is specified for the design. It may be noted here that in case the limiting value of the cracking stress, sigma CR, that is specified for the concrete in the design statement or the design parameters represented by equation A is 0. That is, in case the cracking stress or the limiting value of the cracking stress of concrete is specified as 0 in equation A, then the pre-stressed concrete beam illustrated in the present slide and considered in the solved example herein will be designed to remain free from tensile stresses at any and all locations by virtue of the pre-stressing. In case the necessary and sufficient condition or the limiting condition represented by equation A or relationship A is satisfied by the design by selecting the appropriate combination of the pre-stressing force Tp in the pre-stressing cable or the tendon and the eccentricity E of the pre-stressing tendon or the cable that is constant due to the straight tendon or cable profile. And hence the objective or the of the solved example considered in the present slide, or the design objective depicted or represented by the limiting condition in equation A will be fulfilled. Continuing our discussion on the structural benefits or structural advantages of pre-stressed concrete in comparison to reinforced concrete, based on the elastic behavior of pre-stressed concrete beam elements, recall that the most fundamental and foremost structural benefit or advantage of pre-stressing concrete in a pre-stressed concrete beam element in comparison to a corresponding reinforced concrete beam element is that in case of fully pre-stressed concrete beams, the concrete section or the cross-sectional area of the concrete is more effectively utilized in comparison to a corresponding reinforced concrete element, since the pre-stressed concrete beam element can be designed to remain uncracked or even free from tensile stresses by design, by selecting the appropriate combination of the pre-stressing force in the pre-stressing steel tendon or steel cable TP and the eccentricity E of the pre-stressing cable or tendon with respect to the centroidal axis of the pre-stressed concrete beam section. Thus, proceeding with the solved example presented in the previous slide for the purposes of illustrating the first and foremost structural benefit or advantage of pre-stressed concrete beam elements, the normal or direct bending stress at any location X or Y with respect to the choice of the coordinate axis displayed in the figure on the previous slide, denoted as sigma x with arguments x and y, where the notation sigma signifies the normal or direct stress, while the subscript x signifies that the normal or direct stress is in the direction of the centroidal axis x in the selected coordinate axis x and y, can be calculated by superimposing or adding the contribution or the effect of the bending moment, that is the bending moment m subscript z superscript q, signifying that the bending moment is about the z-axis in the selected coordinate axis, while the superscript q signifies that the bending moment is due to the externally applied uniformly distributed load of intensity Q at the coordinate x of interest divided by the second moment of area of the cross section of the pre-stressed concrete beam, denoted as IZZ, where the notation capital I signifies the moment of inertia, while the subscript ZZ denotes that the second moment of area is about the z-axis times y, that is the coordinate of the point of interest where the normal or direct bending stress is to be calculated along the y-axis, that is the height above the centroidal axis, minus the pre-stressing force that is transferred from the pre-stressing steel cable or tendon to the concrete in the pre-stressed concrete beam element divided by the area of cross section of the concrete beam element plus another component due to the pre-stressing force that is equal to the pre-stressing force transferred from the steel to the concrete in the pre-stressed concrete beam element times the eccentricity of the pre-stressing force or the pre-stressing cable or tendon with respect to the centroidal axis of the pre-stressed concrete beam divided by the second moment of area of the cross section of the pre-stressed concrete beam element IZZ times y, that is the y coordinate or the height of the point of interest at which the normal or direct stress in the pre-stressed concrete beam element is to be calculated. The physical interpretation of equation B, thus expressed in the present slide, is that the normal or direct bending stress in the pre-stressed concrete beam element sigma x at any location or coordinates x and y can be expressed as a sum of two components. One, that is due to the externally applied bending moment due to the external uniformly distributed load Q, and the second component of the normal or direct bending stress sigma x that is generated by the pre-stressing force in the pre-stressing steel cable or tendon that is transferred to the concrete, denoted as capital T subscript P, which itself can be decomposed or divided into two subcomponents, one that results in a uniformly compressive axial stress in the pre-stressed concrete beam at the section X of interest, and the second subcomponent, which is due to the bending moment induced by the pre-stressing force in the pre-stressing steel cable or tendon, Tp acting at an eccentricity P with respect to the centroidal axis of the pre-stressed concrete beam. Hence, combining the two components and their subcomponents thereof, one can obtain the total normal or direct bending stress at any location xy of the pre-stressed concrete beam element due to the contribution of the externally applied bending moment Q, that is mz Q, as well as the pre-stressing force Tp in the pre-stressing cable or tendon acting at an eccentricity E with respect to the centroidal axis of the pre-stressed concrete beam element. And the total stress at any location or coordinates x and y, that is the total normal or direct bending stress sigma x at any general location x and y with reference to the choice of coordinate axis displayed in the figure on the previous slides, can be related to the externally applied bending moment mzq and the pre-stressing force Tp and the eccentricity of the pre-stressing tendon or cable with respect to the centroidal axis as illustrated by the relationship given in equation B. It is worthwhile to mention here that the sign convention that has been used or followed to calculate the normal or direct bending stress sigma x at any general coordinates x and y of the pre-stressed concrete beam element displayed in the previous slide is that tensile stresses are considered to be positive, and as displayed in the previous slide, sagging moments are positive or considered to be positive, while shear forces are considered to be positive and the corresponding shear stresses are assumed to be positive if the shear force or the shear stress is acting upwards on the left face of the differential element and acting downwards on the right face of the structural differential element. Please refer to the sign convention displayed in the previous slide. Therefore, in order to achieve the limiting condition for which the prestressed concrete beam is designed to remain uncracked, as mentioned in the previous slide, and highlighted by equation A in the previous slide, the prestressed concrete beam can be designed to remain uncracked if the limiting condition that the normal or direct bending stress at x equal to 0, that is the midspan, and the extreme tension fiber, that is y equal to minus d by 2, does not exceed the limiting value of the cracking stress of concrete or the cracking strength of concrete. It is worthwhile to note here that in case the cracking stress of concrete or the cracking strength of concrete, denoted as sigma CR, is specified as 0 in the limiting condition, then the prestressed concrete beam will be designed to remain free of any tensile stresses and therefore also uncracked in the range of working or service loads, provided that equations A presented in the previous slide defining the limiting condition for an uncracked section and equation B presented in the current slide defining the applied normal or direct bending stress at general coordinates x and y for the values of x equal to 0, that is the midspan, and y equal to minus d by 2, that is the extreme tension fiber at the midspan, are both satisfied or solved simultaneously for the special case of the cracking strength or cracking stress of concrete sigma C are specified as 0. As mentioned earlier, in case of fully pre-stressed structural beam elements wherein the limiting condition presented herein is fulfilled by selecting an appropriate combination of the pre-stressing force in the pre-stressing tendon or cable denoted as capital T subscript P and the eccentricity E of the pre-stressing cable or tendon at the midspan by design. The pre-stressed concrete beam thus designed remains uncracked in the working or service range of loads. And for the special case wherein the cracking stress or the limiting value of the cracking strength sigma CR is specified as 0 in equation A, that is the limiting condition expressed in the previous slide as well as here in the present slide is specified as 0, then the pre-stressed concrete beam element considered in the solved example will be free from tensile stresses at any and all locations. In order to summarize our discussion on the first and the foremost benefit of pre-stressing in a pre-stressed concrete beam in comparison to a corresponding reinforced concrete beam, based on the physical explanation or the physical reasoning of the structural effect of pre-stressing in the stress or axial tensile or the uniaxial tensile stress response of the concrete in the pre-stressed concrete beam element considered in the solved example in the previous slide. The pre-stressing force denoted as T subscript P induces two types of effects, or two distinct structural effects in the concrete in case of the pre-stressed concrete beam element. first structural effect is the uniform axial compressive stress that is generated by the pre-stressing force Tp as depicted in this figure at any general cross-section X of the pre-stressed concrete beam, and the uniform axial compressive stress that is generated by the pre-stressing force Tp at any general location X in the pre-stressed concrete beam element can be calculated as minus Tp divided by the area of the cross section of the pre-stressed concrete beam at that location. The minus sign signifies that the uniform axial compressive stress is compressive, while the second effect, that is the second structural effect of the pre-stressing force Tp in the pre-stressed concrete beam is due to the eccentricity of the pre-stressing force or the pre-stressing tendon or cable with respect to the centroidal axis of the pre-stressed concrete beam, denoted as E, which may be a variable or which may vary with the coordinate x in general. That results in a bending moment in the pre-stressed concrete beam at the location X due to the eccentricity E at that location X of the pre-stressing force Tp. As a result, the pre-stressing force Tp also induces normal bending stresses as depicted in this figure. Due to the pre-stressing force acting at an eccentricity with respect to the centroidal axis of the pre-stressed concrete beam. The sum of these two effects on the normal or direct bending stress are denoted as sigma subscript x superscript p, where the superscript p signifies that the component of the normal or direct bending stress sigma x is due to the pre-stressing force acting at an eccentricity E with respect to the centroidal axis of the pre-stressed concrete beam. When added to the normal or direct bending stress, due to the externally applied bending moment, that is, the bending moment induced by the externally applied uniformly distributed load of intensity Q and denoted as M subscript Z superscript Q, the total or the resultant normal or direct bending stress sigma x at any general location or coordinates x and y is considerably less in comparison to the corresponding reinforced concrete beam. In other words, mathematically, the total normal or direct bending stress sigma x due to the combined action of the externally applied uniformly distributed load Q at any location or coordinates x and y when combined with the normal or direct bending stress sigma x due to the pre-stressing force in the pre-stressing tendon or cable denoted as sigma x superscript p, resulting in a resultant or total value of sigma x that is the normal or direct bending stress due to the combined or sum total of Q and P, that is combined action of the externally applied uniformly distributed load Q and the pre-stressing force P at any general or location or coordinates x and y which is significantly less in comparison to the corresponding reinforced concrete element based on the sign convention that tensile normal stresses or tensile direct stresses are positive. Proceeding to the second structural benefit or advantage of pre-stressed concrete beams in comparison to the corresponding reinforced concrete beams, that is the structural advantage or benefit of pre-stressing concrete. The pre-stressed concrete beams display a superior shear resistance or a higher shear strength in comparison to the corresponding reinforced concrete beam, fundamentally because the pre-compressive stress or the initial compressive stress depicted by the minus sign in this figure or these two figures due to the pre-stress in the concrete denoted as sigma x superscript p with the arguments x and y, counteracts or reduces the principal tensile stress that causes diagonal cracking of the concrete under combined shear and bending. And the structural benefit or the structural advantage number 2, thus stated, will be demonstrated with a physical explanation or physical reasoning by providing a mathematical proof of the statement that is statement number 2, stating the second structural benefit or structural advantage of pre-stressed concrete beams in comparison to reinforced concrete beams. It is worthwhile to mention here that the mathematical proof provided in the next slide for the second structural benefit or structural advantage of pre-stressing concrete in case of pre-stressed concrete beams in comparison to the corresponding reinforced concrete beams. Based on the physical explanation of the particular structural advantage or structural benefit is also the solution to question number 2 of assignment number 2 that will be assigned in due course. In other words, the mathematical relationships for the principal tensile stresses and compressive stresses based on mechanics of materials or solid mechanics in terms of normal bending stresses and shear stresses that are presented in the next slide as part of the mathematical proof of the statement of the second structural benefit or structural advantage stated herein in the present slide. Constitute the theoretical formulations that are required for solving question number 2 of assignment number 2 that will be assigned in due course. Continuing our discussion on the structural benefits or the structural advantages of pre-stressed concrete in comparison to reinforced concrete, the mathematical proof for the second benefit, that is point number 2 presented in the previous slide, stating that pre-stressed concrete elements that are subjected primarily to bending or flexural stresses, defined as pre-stressed concrete flexural elements or pre-stressed concrete beam elements, display a superior shear resistance in comparison to the corresponding reinforced concrete beams or reinforced concrete flexural elements, since the pre-compressive stress or the pre-stress induced by the pre-stressing steel in the pre-stressed concrete beam elements counteracts and reduces the principal tensile stresses, thus resulting in a higher or larger value of the shear force or the externally applied imposed load that is required to induce diagonal cracking that is cracking of concrete under the combined action of flexure or bending as well as shear. With that recap, let us proceed to the mathematical proof of the statement that presents the second structural benefit just mentioned and also listed in the previous slide. The principal tensile stresses and the principal compressive stresses based on fundamentals of mechanics, essentially equations of statical equilibrium of a differential concrete element, that is a concrete element with differential dimensions dx and dy in the pre-stressed concrete beam considered in the example presented in one of the previous slides, that is simply supported with a span length L, that is the unsupported length between the adjacent supports, which are simple supports as L, and subjected to a uniformly distributed load representing the permanent dead load and the live load or the imposed load of intensity Q in kilonewton per meter, for example, in SI units, may be obtained using the well-known equations that are available or documented in all standard textbooks based on mechanics of materials or statics. For example, textbook by Irving Shames or the textbook by R. Hibbler that provide the relationships based on considerations of statical equilibrium of a differential concrete element in such a beam which is simply supported and subjected to a uniformly distributed load as expressed in this equation or relationship relating the principal tensile and compressive stress sigma 1 and 2 respectively at any general location or coordinates x and y in the Cartesian coordinate system with the choice of coordinate axis illustrated in this figure, as detailed by the well-known relationship documented by all standard texts between the principal tensile and compressive stresses sigma 1 and 2 with the normal bendings or direct bending stress sigma x and the shear stress tau xy depicted in this figure for the differential concrete element in the pre-stressed concrete beam displayed in the figure on the present slide. Wherein the state of stress in the differential element of differential dimensions dx and dy depicted in this figure, where the differential dimensions dx and dy are both infinitesimally small and therefore tending to 0, may be obtained by computing the normal or the direct bending stress sigma x using equation B for the normal bending or normal direct stress at any general location or coordinates x and y presented in one of the earlier slides for the pre-stressed concrete beam considered in the present example. Referring to equation B presented in one of the previous slides relating the normal or direct bending stress at any general location or coordinates x and y in the pre-stressed concrete beam to the bending moment, that is the externally applied bending moment due to the external uniformly distributed load of intensity Q, as well as the pre-stressing force in the pre-stressing steel that is transferred to the concrete after the pre-stressing operation and thus inducing a pre-compressive or pre-stress in the concrete, as well as the eccentricity E of the pre-stressing force, that is the eccentricity of the pre-stressing tendon or cable with respect to the centroidal axis X of the pre-stressed concrete beam as illustrated or expressed by equation B presented in one of the earlier slides. While the shear stress tau xy can be calculated at any general location or coordinates x and y in the pre-stressed concrete beam using the well-known equation for shear stress that is documented or available in all standard texts. For example, textbooks on mechanics or statics by Irving Shames or R. Hibler, relating the shear stress at any general location or coordinates x and y denoted as tau xy with the shear force at the x coordinate, that is at the section of interest along the centroidal axis x, denoted as capital V subscript y, where the notation capital V denotes shear force and subscript y denotes that the shear force is acting in the y direction. Argument x denotes that the shear force is being considered at the section x or the location x or coordinate x with reference to the choice of coordinate axis times the area A subscript I as illustrated in the figure in one of the previous slides. Above, that is the area of the concrete section above the horizontal section y at the coordinate y of interest, divided by the product of the width of the cross section assumed to be constant, as in case of the prismatic rectangular cross section for the pre-stressed concrete beam considered in the present example, times the second moment of area or the moment of inertia about the z axis denoted as IZZ, where the z axis is the coordinate axis pointing out of the plane of the paper for the choice of the coordinate axis selected for the analysis of the present pre-stressed concrete beam. Well, the relationship for the shear stress tau xy at any general location of coordinates x and y is well documented in any standard textbook on mechanics, and the derivation of the equation is also available in both the textbooks on mechanics of materials mentioned in the previous slide. Hence, proceeding with the well-documented relationships for the normal or direct bending stress sigma x at any general location of coordinates x and y, as well as the relationship for the shear stress tau xy at the same general coordinates x and y, and substituting those into the relationship expressed in the present slide for the principal tensile and compressive stresses sigma 1 and 2 respectively at the same coordinates x and y, one can obtain the values of the principal tensile and compressive stresses sigma 1 and 2 respectively at the general coordinates x and y of interest. A word about the sign convention. The sign convention that is assumed in the present formulations based on fundamentals of mechanics is that the sagging moments are considered to be positive while computing the normal or direct bending stress sigma x, and the normal or direct bending stresses are assumed to be positive when they are tensile, that is tensile normal or direct stresses are considered positive, while shear forces and shear stresses, that are denoted as capital V, Y, V subscript Y, and tau xy respectively, are considered to be positive when acting upward on the left face of the differential element and downward on the right face of the differential element. Hence, computing the normal or direct bending stresses sigma x at as well as the shear stresses tau xy at the representative locations of the pre-stressed concrete beam. For example, at the simple supports at which the bending moment or the externally applied bending moment is 0, and the midspan at which the externally applied bending moment m subscript z is the maximum, while the shear force is 0. As well as the extreme fibers, that is at the y coordinate equal to plus minus d by 2, that are the free edges of the pre-stressed concrete beam, or the extreme fibers of the pre-stressed concrete beam, at which the shear stresses are 0, while the normal or direct bending stresses are maximum in their absolute value. That is, the tensile and the compressive normal or direct bending stresses are maximum. And the neutral axis at which the normal or direct bending stress sigma x is 0, while the shear stress tau xy is maximum, as depicted by the plot of the shear stress over the depth of the cross section presented in the previous slide. Therefore, computing and considering the values of the normal or direct bending stresses at various representative locations just mentioned, and the values of the shear stresses tau xy also at the various representative locations just mentioned, that is at x equal to plus minus L by 2 and x equal to 0, y equal to plus minus d by 2 and y equal to 0, or y equal to the y coordinate of the neutral axis if the y coordinate of the neutral axis is not 0 in general. One can compute the numerical values of the principal tensile and compressive stresses denoted as sigma 1 and 2 at general location or coordinates x and y, including the representative locations just discussed, as well as the angle of inclination phi of the principal tensile stress with respect to the longitudinal or horizontal coordinate axis x, acting on the differential concrete element at any general location of coordinates x and y, using the second classical relationship or classical equation, that defines the angle of inclination of the principal tensile stress, and therefore the angle of inclination of the principal compressive stress also, since the principal tensile stress sigma 1 and the principal compressive stress sigma 2 are orthogonal to each other or perpendicular to each other. The second equation provided in the present slide, relating the angle of inclination theta of the principal tensile stress sigma 1 to the shear stress tau xy and the normal or direct bending stress sigma x at any general location of coordinates x and y, is also well documented in standard textbooks. For example, textbook by Irving Shames or R. Hibbeler on mechanics or statics. And the derivation of both the classical equations defining the magnitude or the values, that is numerical values of the principal tensile and compressive stress sigma 1 and sigma 2 respectively, and their direction of the two principal stresses in terms of the angle of inclination of the principal tensile stress with respect to the longitudinal or horizontal axis x are available in both these standard textbooks, can be referred to for the mathematical derivation of these two fundamental equations of mechanics or statics for the principal stresses. Thus, having calculated the numerical values as well as the directions of the principal tensile and compressive stresses sigma 1 and sigma 2 respectively at the representative locations mentioned earlier, using the two classical equations for any general coordinates x and y, one can plot the trajectories of the principal compressive stresses sigma 2 as well as the orthogonal principal tensile stresses sigma 1 in the entire elevation of the beam or vertical cross section of the beam in elevation as depicted in this figure. It is worthwhile to mention here that the representative locations or the representative coordinates x and y mentioned earlier signify or represent the benchmark locations or coordinates for plotting the stress trajectories of the principal tensile and compressive stresses sigma 1 and sigma 2 respectively. For example, the coordinates x equal to plus minus L by 2 representing the simple supports at the two simply supported ends of the beams correspond to a differential concrete element which is in a state of pure shear. Since at the simple supports or the coordinates x equal to plus minus L by 2, that is at the simply supported ends of the beams, the normal direct or normal bending stress sigma x is 0 simply because the bending moment or the externally applied bending moment due to the external uniformly distributed load Q is equal to 0 at the simply supported ends. As a result, substituting the value of the normal bending stress equal to 0 in the classical equation or relationship for the principal tensile and compressive stresses, the principal tensile and compressive stress sigma 1 and sigma 2 work out to be plus minus the shear stress at the location, that is plus minus tau xy respectively. Corresponding to the principal tensile stress sigma 1 and principal compressive stress sigma 2. Further, at the representative location of the midspan, that is defined by the x coordinate equal to 0, the shear force, that is the externally applied shear force denoted as V subscript y at x equal to 0 is 0 based on simple statics for a simply supported beam subjected to a uniformly distributed load. As a result, the shear stress tau xy given by the classical equation for shear stress documented in all the standard textbooks on mechanics of materials also works out to be 0. And thus substituting a 0 value for the shear stress tau xy into the well-known relationship for principal tensile and compressive stress sigma 1 and 2 respectively, the principal compressive as well as the principal tensile stress sigma 2 and 1 respectively are 0 and sigma x respectively. That is, substituting the value of 0 for the shear stress tau xy into the well-known equation for principal tensile and compressive stress sigma 1 and 2 respectively, the principal tensile and compressive stress sigma 1 and 2 can be computed as sigma x and 0 respectively. Further, at representative locations corresponding to the y coordinates, that present the typical or representative state of stress in the differential concrete element, for example, at the extreme fibers defined by the coordinates y equal to plus d by 2 and minus d by 2, that is the free edges of the simply supported beam, the shear stresses tau xy at the y coordinates plus minus d by 2 are intuitively 0, since the y coordinates y equal to plus minus d by 2 represent the free edges of the simply supported beam, and therefore the angle of inclination phi as given by the second classical equation defining the direction of the principal tensile and compressive stresses work out to be 90 degrees and 0 degrees respectively, corresponding to y equal to plus d by 2 and minus d by 2 respectively. Furthermore, at the other representative value of the y coordinate, that is y equal to the y coordinate of the neutral axis of the pre-stressed concrete beam, that is the y coordinate of the fiber or the y coordinate at which the normal or direct bending stress are 0 based on the definition of neutral axis. The normal or direct bending stress sigma x is 0. thus resulting in the value of the angle of inclination phi of the principal tensile stress with respect to the x-axis equal to 45 degrees. And since the principal compressive stress, principal tensile stress and principal compressive stress are mutually orthogonal or perpendicular to each other, the value of phi thus computed for the representative y coordinate, that is the y coordinate corresponding to the neutral axis at which the normal or direct bending stress is equal to 0, defines the direction of both the principal stresses, that is principal tensile stress sigma 1 and principal compressive stress sigma 2. The directions or the trajectories of the principal tensile and compressive stress at intermediate locations or intermediate x and y coordinates can be interpolated to arrive at this schematic diagram for the trajectories of the principal tensile and compressive stresses by interpolating between the values obtained at the representative locations or coordinates x and y just explained. Returning to the mathematical proof of the second benefit or advantage of prestressed concrete in comparison to reinforced concrete, that is point number 2 mentioned in the previous slide as one of the important structural benefits or structural advantages that are achieved by pre-stressing concrete. Based on the treatment of the classical equations for the numerical values of principal tensile and principal compressive stresses sigma 1 and 2 respectively at any general coordinate x and y, as well as the direction of the two principal stresses at any general location of coordinates x and y, one can intuitively visualize that the principal tensile stress at any general location of coordinates x and y due to the combined action of the externally applied uniformly distributed load Q plus the pre-stressing force Tp will always be less than the principal tensile stress sigma 1 due to only the action of the externally applied UDL or uniformly distributed load Q at that location or coordinates x and y based on the equation presented in the previous slide, that is equation number B, depicting the principal tensile stress due to the combined effect of the UDL-Q and the pre-stressing force Tp as well as the principal tensile stress sigma 1 due to the effect of the UDL-Q only. And the physical reasoning for this inequality is that the normal or direct bending stress sigma x due to the combined effect of the UDL-Q and the pre-stressing force Tp denoted as sigma x, sigma subscript x, superscript q plus p, is always less than the normal or direct bending stress sigma x due to the effect of the UDL-Q only, denoted as sigma subscript x superscript q. And substituting the inequality on the right hand side, that is the inequality between sigma subscript x q plus superscript q plus p and less than, that is less than sigma subscript x superscript q at any general location of coordinates x and y into the classical equation for the principal tensile and compressive stresses. One can easily verify that the principal tensile stress sigma 1 due to the combined effect of the UDL-Q plus the pre-stressing force Tp at any general location x and y denoted as sigma subscript 1 superscript q plus p will always be less than the principal tensile stress sigma 1 due to the effect of the UDL Q denoted as sigma subscript 1 superscript q at any general location or coordinates x and y. Based on the sign convention that tensile stresses are considered positive, or tensile normal or tensile direct stresses are considered positive. Hence, in conclusion, the principal tensile stress at any general location of coordinates x and y in a pre-stressed concrete beam will always be less than the principal tensile stress sigma subscript 1 superscript q in a corresponding reinforced concrete beam, since a reinforced concrete beam is subjected only to a uniformly distributed load and there is no pre-compressive stress due to any pre-stressing force in a reinforced concrete beam. Hence, the uniformly distributed load Q, or the intensity of the uniformly distributed load Q, that is required to induce diagonal cracking or shear cracking. That is, the intensity of the uniformly distributed load Q that is required to reach the limiting condition for diagonal or shear cracking is much higher in case of the pre-stressed concrete beam in comparison to the corresponding reinforced concrete beam, simply because the principal tensile stress sigma 1 that is required to cause shear failure due to diagonal cracking will always be higher or rather will always require a larger or higher value of the UDL then the UDL required to cause shear failure due to diagonal cracking in case of the corresponding reinforced concrete bar. In conclusion, therefore, since the principal tensile stress due to the combined effect of the uniformly distributed load of intensity Q plus the pre-stressing force Tp in case of the pre-stressed concrete beam is always less than the principal tensile stress sigma 1 due to the effect of UDL alone in case of the corresponding reinforced concrete beam. Shear failure due to diagonal cracking of the concrete that occurs at the limiting condition when sigma 1 exceeds the cracking stress or the fracture strength of concrete. Will always be less than the UDL that is, or the intensity of UDL that is required for reaching the limiting condition of shear failure due to diagonal cracking in case of the reinforced concrete beam.